Hello everyone. Today we're going to be going over a new case study. Today's case study will be an application in the oil and gas industry that can be also used in many other industries as well. We're going to be going over why dynamic image analysis is a necessary complementary technique to laser diffraction. The samples we're going to be looking at today are proppants. Proppants are solid materials that are used to keep hydraulic fractures open in the oil and gas industry. These are used in different reservoirs, typically unconventional reservoirs, and again, it's used to extract materials from the ground. The proppants that are generally very round in shape are added to fracking fluids. These fracking fluids can vary in different types of applications. Users use different types of fracking fluids depending on the needs that they have. The fracking fluids that are used in combination with the proppants are going to be dependent on the viscosity. Obviously, the more viscous the fluid, the more concentrated the proppant can be, but then that's going to be more difficult to pump. There's also looking at the energy, the pressure demands for the pump rate, and always looking at different rheological factors in selecting the proppants to use and the fluids to use. In this case study, we're going to be looking at a practical customer sample where proppants were being used and they were being measured for size using sieving and laser diffraction. We're analyzing these particles for shape, being that circularity is important, but then we discovered something along the way that they were not expecting, but it made more sense that we'll discuss at the end. So the approximate size that these proppants have were about 700 microns in sieving, but they were about 500 microns using laser diffraction. It's important to note that different techniques will almost always give slightly different results, especially when the particles are not round. Our analysis was done using both laser diffraction and dynamic imaging to obtain the shape information. They needed as well to have correlation to laser diffraction, so that's why we also ran it on a laser diffraction system. So to compare, give a little bit of insight on the different techniques, give it a really brief overview of laser diffraction. A typical laser diffraction system is shown here, a schematic where you have particles that are going to be going through a fluidic or a dry system. The light or a laser will shine on the particles, and then there will be a diffracted light at different angles. The light energy observed by these detectors is proportional to the volume of the particles. So as a result, laser diffraction results are reported as volume-weighted results. Because the diffracted light is proportional to the particle's volume, results assume that all particles are spherical in shape and reported as equivalent spherical diameter. It's also important to note that as particles become smaller and smaller, their scattered light intensity is weaker at the higher angles. Giving a brief overview of dynamic image analysis, dynamic imaging uses a high-speed camera and a flashing light to capture particles that are in motion. These high-resolution images are converted to binary, where real-time particle data is calculated and reported. The real-time data is reported, and thumbnail images of each particle is saved, which is always good for objective evidence. Dynamic imaging, being a number-based instrument, can count and give concentration data, which is the particles per milliliter that are found. And number-based techniques, they will count and measure all particles within size limits, no bias to smaller or larger particles. And the particle size distribution can be represented either in a volume-weighted distribution, similar to that of laser diffraction, or a number-weighted distribution. So now that we discussed both volume and number weighted, let's talk about that just a little bit more in a practical example. Looking at this practical example, this is actually the same sample that we're looking at, but the graph on the left you'll see is a number weighted distribution. The graph on the right is a volume weighted distribution. To explain the difference between a number weighted distribution and a volume weighted distribution, here's a graphic that I created many years ago to help. If we use three different samples, sample 1, sample 2, and sample 3, each sample is going to have four particles. Right? So sample 1 has 4 particles, sample 2 has 4 particles, and sample 3 has 4 particles. If we calculate, and obviously sample 1 is 1 micron in diameter, sample 2 is going to be 2 microns in diameter, and sample 3 is going to represent 3 microns in diameter. When we calculate the volume of each particle and then actually calculate the volume of all 4 particles, you can see that when you calculate the volume of 4 small particles here in sample 1, it's going to represent a 16 versus sample 2, 128 versus sample 3, 432. So basically, if you look at the results, when you look at a number weighted distribution, you're going to notice that when you look at the 1 micron, 2 micron, 3 micron sample, they're going to be represented equally in a number weighted distribution because they're being represented by number. So all the 4 particles are going to be here, same as here, and their 4 3 micron particles are going to be here. However, when you look at a volume weighted distribution, the volume weighted distribution will be a 16 here, a 128 here, and a 432 here. So the volume weighted distribution will actually look at the reporting based on volume. This is very useful, especially when you're looking at agglomerates in samples. So both are very important, as we'll see in the next slide. So coming back to this slide, you can see that the number weighted distribution for this sample definitely shows all of the finds, which are important to always see. And then the volume weighted distribution shows you some of these peaks. For example, this 300 micron particle might be 1 or 2 agglomerates. You may not see that on a number weighted distribution, but if you switch over to a volume weighted distribution, you will see it. So both distributions are very important. Going back to the case study, what we're going to be looking at is these proppant samples, which you could see the images here on the right. And we're going to be looking at how they report in dynamic imaging and also how they report in laser diffraction, which is the graph on the left. What we're running here is a proppant material, which is going to be analyzed on the right with a laser diffraction system and on the left with a dynamic image analysis system. The sample is the same sample that's being run through both systems, and the goal here is to show how a number-based technique, being the one on the left, a dynamic image analysis system, is a necessary complement to a laser diffraction system, which is a volume-based system, the system on the right. And what we will see is the fact that we do measure the larger particles, as you can see on the screen on the left, but it will be unable to measure the smaller particles due to the weakness in the scattering intensity of the smaller particles. And what I've noticed is there are definitely some small particles in there. If I convert this over to a volume weighted distribution, we'll start seeing some similarity in between what we're seeing here at about a D50 of 556, and here we're looking at somewhere in the 500s. So that's the first measurement. So as you can see here, we're already running 37,000 particles per ml, a total of 3,000 so far. And again, we're looking at a volume weighted distribution, comparing it to laser diffraction. But when you look at the Hydro Insight, we go to number weighted, we definitely see there's a large population of small particles. These are all these small particles that you see here. So let's take a pause and we'll come back to this. As you can see here on the laser diffraction system, we have a D50 of about 495. When we look at dynamic image analysis, we have a D50 of about 544. A little bit different, not very surprising given that they are different techniques. and the particles aren't completely round. If you look at the circularity, a majority of the circularity is, the mean circularity is about 0.73. So because the particles aren't perfectly round, there is going to be a little bit of an irregularity in size. So I think that's why you're going to see a slight difference in particle size, ECA diameter, equivalent circular diameter, volume weighted from dynamic image analysis compared to laser diffraction. What is interesting though is in laser diffraction there is no scattering, no reporting of particles below the main peak. Whereas when you look at the number weighted distribution for image analysis, there are a larger number of particles in the smaller size range. Neither one is wrong. The reason is because of the volume weighted distribution, and the weak scattering intensity does not allow laser diffraction to see these particles. These particles are actually there. We can actually view them not only in the image, but we could also view them in the thumbnail images. So in the thumbnail images, yeah, there are going to be some doublets and triplets, but definitely we could see all these larger particles when they are singlets. They're definitely in the 500 micron range, 600, but definitely they are irregular in size. When we started looking at some of the smaller thumbnails, definitely found a couple of bits of fiber in there. It's a bit bizarre, but as you can see, there are definitely small particles in there in the sample. The fact that we actually had small particles and they were not seen by laser diffraction doesn't necessarily mean that they're not there. This is why this is a good complement to have image analysis as a complement to laser diffraction. With respect to the application that we're working on here, the vast amount of small particles is what was causing the rheological differences in the fracking material in the proppants. And the fact that they were using two techniques, sieving and laser diffraction, they could not see these small particles. This is why their viscosity was a bit irregular, and it's because they couldn't see these small particles. Therefore, a number-weighted technique such as dynamic image analysis is a great complement for laser diffraction. I hope this helps. Thank you. So in conclusion, laser diffraction is an excellent tool. It's been very well established for many decades, and it's an excellent technique for particle size analysis. Also, what we've learned is having a number-weighted statistical technique is also important as having a volume-weighted technique like laser diffraction. Having both gives you a very clear view of your entire sample, which is very important. You may be missing some critical performance issues by not having both. In the case of this application note or this case study, the rheological differences were brought about by these tiny particles that were not being observed by laser diffraction, and it was a very interesting observation that the customer noticed and realized that these small particles and their presence, even though not detected by sieving or laser diffraction, is what was affecting the rheological properties of the suspension of these particles. Also, in conclusion, dynamic image analysis, obviously great complementary tool to laser diffraction. It not only shows the number weighted statistics, but it also shows particle count, particle concentration, which is the number of particles of interest per milliliter. It shows thumbnail images. We can classify particles with dynamic image analysis by different shape parameters and many other benefits. I hope this was helpful. Thank you for your time. Please reach out to us if you have any questions. Thank you.